I'm going to talk about some work that we've recently completed. It's not published yet. It's been submitted for publication, but it's not out yet. This is some work that was funded partly by the Commission on Water Resource Management, partly by the Park Service, and also partly by the USGS. Prior to a few years ago, there were two known groundwater systems in the Kona area. And they're separated by that black dashed line that I've shown there. Seaward of that black line, we noticed that wells have water levels typically of only a few feet above sea level. Today you saw some of the Anklin pools. Those water levels in those pools are probably about a foot to a foot and a half above sea level. But even if you go further inland, water levels are probably less than 3 feet above sea level if you remain seaward of that black line. In the early 90s, a number of wells began to be drilled in that inland area, shown by those blue dots. And it was discovered that water levels were substantially higher, typically tens to hundreds of feet above sea level. So there's something going on there. There's a geologic structure. We don't know exactly what it is, but something that's of lower permeability than the aquifer itself exists that causes this head change. In terms of the coastal system, those red dots that I've shown, this is kind of a cross-section of what that groundwater flow system looks like. It consists of brackish water, and I've depicted there an Anklin pool. The Anklin pools basically are depressions in the ground surface that tap into the water table. The brackish water is underlain by salt water, and that salt water actually circulates underneath the brackish water lens. Okay, next slide. In terms of the inland high-level groundwater system, we don't know exactly what's causing it. There may be some low permeability intrusive dikes. These are kind of vertical sheets of intrusive volcanic rock. The middle panel shows faults that could be causing these head discontinuities. And also in the bottom picture, it shows buried lava flows. It could be also maybe ash layers or weathered rock that form a low permeability contrast in the aquifer that causes this water level change. We don't know what it is yet, but hopefully in my lifetime we'll figure it out, but I'm not convinced that we will. Next slide. Okay, a few years ago, a deep well was drilled, and that was drilled under the guidance of Tom Nance, and he was kind enough to share his data. It was a tremendous well that was drilled. It's very deep, and it provides a wealth of information. What I've shown here is a plot of the salinity with depth. So on the vertical scale is the depth, and on the horizontal scale is the salinity that increases as you move towards the right. So if you look at that pink line near the top, on the vertical scale near zero, you start off at somewhat brackish water, and then it starts increasing with salinity increases as you go down. But it's a very gradual increase, and that's an important point to make. It takes about 500 feet into the water until you start hitting more salty, almost pure salt water. As the well was drilled deeper, down below 1,000 feet below sea level, it hit a zone of fresh water. That zone was relatively thin, on the order of maybe 10 meters or thick or so, and it was likely confined by low permeability zones both above and below it, because below that fresh water, the well encountered salt water again. Next slide. The Kamakana profile is actually somewhat unique in terms of what we know from comparable wells in similar settings where you have a very thin freshwater lens. Even as you move further south in Keauhou, the state has a deep monitoring well there that they log, and you can see that there's quite a difference in the shape of the profiles. The pink one, it takes a very long depth increment for it to reach salt water. It takes about 500 feet, whereas if you look at that green line, it's reaching salt water within the first 150 or 200 feet. Very different. The green line is more characteristic of other wells that we have, other deep monitoring wells that we have in these thin freshwater lenses. They don't have that long, drawn-out tail in the profile. It takes very extensive transition zone to saltwater. And that is very much consistent with some deep source of fresh water entering into the area of the Kamakana well that's contributing to that slow tailing off of the brackish water into salt water. Next slide. Okay, so what is going on with that Kamakana well? I've kind of shown three conceptual models. The top two are end members, and the bottom one is kind of an intermediate case. Okay, so if you look at the top figure, what I've shown is that all of the water that originates in the high-level system is discharging in that narrow freshwater zone beneath the coastal freshwater lens system. And if those confining units that form that freshwater zone, if those confining units are completely impermeable, then all of that water from the high level area will discharge through that thin zone and discharge at depth offshore. Okay, that's one end member. In the middle slide, I've showed the other end member where water can discharge from the high level system, and let's say those confining units pinch out before they reach the coast. Well, then all of that water from the high level system then is going to eventually contribute to the freshwater lens system near the coast, and that which the park relies on in terms of its water resources. So that's the other end member. The bottom slide is kind of a combination. It's kind of a compromise situation where some of the water from the high level system discharges offshore at depth through that thin confined zone, and some of it contributes to the freshwater lens system. Okay, so those are kind of conceptually what may be going on. We don't know exactly which one of those is happening, although based purely on that Kamakana well profile, it would suggest that it's probably not the top one. Okay, next slide. Okay, so that brings us to our study that we did. The objective of our study was to evaluate the connection between the high level and the coastal freshwater lens system. And we actually used a number of geochemical tracers, but none of them were as enlightening as the stable water isotopes. So that's what I'm going to talk about today. Next slide. Okay, so this is a map of our sampling network. We sampled 7 wells in the high level system, shown by those orange squares that are inland of that black line, dashed line. We sampled 11 wells in the coastal system, and shown as those pink squares. And then the circles represent pond and pool sites that we sampled, and also a couple of ocean sites. We also set up a transect up Hualalai of precipitation collectors, one down at 5-foot elevation, and the maximum went up to about less than 5,000 feet elevation. Next slide. A very brief background on water isotopes. What are they? Well, they're just isotopes of an element. They have the same number of protons, but they have a different number of neutrons. So hydrogen has 2 main isotopes, protium and deuterium. Protium has no neutrons, and deuterium, which is H2, has 1 neutron. Similarly, oxygen has 2 main isotopes, O16 and O18, and they differ in the number of neutrons. Next slide. Okay, I'm not going to go too much into the theory of isotopes other than to say that they are kind of diagnostic of the elevation of where the water is distributed. And what's commonly used in the isotope literature is this delta value, and I've shown kind of the equation that is used to define what a delta H value is. It's essentially a comparison of your sample to a standard. If that multiplier there would be 100 instead of 1,000, it would just be a percent difference from the standard. And the standard is actually an ocean water standard. So if you look in the figure, I've shown that the delta H and the delta O are both 0 in the ocean. And that's because the ocean samples would be compared to ocean water, so there's no difference. But as you move up slope, due to fractionation and evaporation processes, what happens is that the rain that falls on the land surface becomes more depleted in some of these isotopes, so that as you move further up slope, you get more and more depleted rain, so that the delta numbers actually get more and more negative as you go higher and higher in elevation. So that's just kind of the background that you need to somewhat understand to look at the results that I'll show soon. Okay, next slide. Okay, so this graph here shows results of the precipitation samples that we collected, and I plotted the delta H on the vertical scale and the delta O on the horizontal scale, and they kind of follow a trend line. And what you can see is that that one blue dot that's kind of towards the bottom left of the graph, that was the most negative sample, and that's at the highest elevation. As you move towards the upper right of the graph, that red square, that was collected at the lowest elevation, and so it's closest to a 0, value, closest to the ocean water value. But in general, as you go towards higher elevations, you're getting into the more negative numbers. The samples that we collected for this study, the rainfall samples that we collected, we only were able to collect for about a year. Craig Glenn and Joe Fackrell, they've been collecting rainfall for over 2 years, and they might have some improved relations that can be used for looking at some of these results. Next slide. Okay, so I've shown here again that the data points are the points that we collected. The lines that I've shown here are published lines showing how the hydrogen and the oxygen isotopes vary with each other. So that black line on the bottom is a global meteoric water line. It's not necessarily applicable to the situation in Hawaii. There have been a number of local studies to define local meteoric water lines, and I've shown those. One of them is from Kona, that was done by Craig Glenn and Joe Fackrell. There's one line from East Maui, which is very close to the Kona line. And then the blue one is from Kilauea on the Big Island. But you can see that the data we collected are kind of following along the trends of those lines. Next slide. Okay, so this plot, switching gears here a little bit, this plot is similar in nature. It's plotting the hydrogen isotopes on the vertical scale and the oxygen on the horizontal scale. But these are now the groundwater samples that we collected. They're not the rainfall samples. I've shown the rainfall lines from the previous graph, but all the symbols that you see here are either groundwater samples or ankle and pool samples or actually ocean samples that we collected. The salient feature is that the orange squares, which represent the samples that we collected from the high-level system, tend to be the more negative, more depleted results. And that's because it's getting from the high-level system, you're getting recharge from higher elevation. As you move toward the upper right of the graph, you start getting into the ocean water samples. You're getting into values closer to 0. The samples don't necessarily follow the local meteoric water lines, and that's because the samples aren't made purely out of rainfall. They get mixed with ocean water. That's why many of the samples that we collected are not fresh water. They're a mixture of fresh and salt water. So they're departing from that rainfall precipitation line. Next slide. Okay, so what I've shown here, and it may be difficult to see, but I've got two maps here. Let's just look at the one on the left. I've plotted next to the orange squares, the wells that we sampled in the high-level system, the aggregate recharge altitude based on some existing published relations for the isotopes versus altitude that we have. And the aggregate recharge altitudes on the left side are, in some cases, very unrealistically high. In some cases, you see it goes up to 11,000 or 12,000 feet, but Hualalai only goes up to 8,200 feet. So clearly, something strange is going on there, and it's probably because we haven't characterized the rainfall, the altitude relation very well on Hualalai yet. So to contrast those altitudes that I've shown on the left, which are developed from trade wind relations, looking at the rainfall, how the rainfall varies in a trade wind regime. If you look at a rain shadow area and apply those relations to the isotope concentrations that we found in the high-level wells, you'll see that we get unrealistically low aggregate recharge elevations. In some cases, less than 1,000 feet, which is not possible because all of those wells are located inland of 1,000 feet anyway. So the take-home message here is that the water samples that we collected from the high level system seem to indicate very high elevation that they're coming from. But you got to take that with a little bit of a grain of salt, because I don't think we've got that altitude relation characterized perfectly yet for Huala line. Next slide. Okay, so what we did then was, with our samples, our isotope samples, we tried to examine what fraction of water was, or where the water was coming from in our samples. Was it coming from the ocean? Was it coming from the high level groundwater? Was it coming from local precipitation? So those are kind of the three end members that we were going to mix together to see how it all played out. And we just isolated our analysis to the area kind of inland from the park, ignoring the area far to the south and further to the north. We're kind of concentrating just in that corridor inland of the park. There are the three end members that we're using then to represent this mixing analysis is the high level groundwater end member, and that was from the Honokohau and the Kalawa wells, I believe. We used a couple of precipitation end members, one at 750 foot altitude and the other at 1800 foot altitude. So one of them is kind of in the middle of the coastal freshwater lens system, and the other would be above the coastal freshwater lens system. We kind of, because there's some uncertainty, we kind of tried to get a reasonable range of precipitation end members. In terms of the ocean end member, we found that there was a difference between some of the shallow and the ocean water and the deep ocean water samples in terms of the isotope makeup, so we tested them both. And what you do in this type of three-component mixing analysis is you form a triangle between your end members. So you can see I've drawn two triangles, and they're actually, because we have four different end members or two each for precipitation and the ocean water, you can actually form four different triangles from all the different end members. But I've just shown two here. And what you do in this analysis is you look where in that triangle your samples fall, and you can compute quantitatively how much of each end member is required to mix to produce the sample concentrations. Okay, so it's a little bit of a mathematical manipulation, but it's not that complicated. If you imagine it being in the middle of a triangle and you're trying to figure out, which end member is it closest to, that's the one that's going to be the greatest contributor to your sample. Okay, next slide. Okay, so we went through some mathematical computations, and this map shows the percentage of fresh water from the high level system from the selected wells that we used in our analysis. So we just isolated the freshwater component of our samples. We eliminated the saltwater component, and we determined how much of it was coming from high level system, and the rest of it would be coming from precipitation locally over the freshwater lens system. And you can see the numbers are kind of all over the place, but typically they're in the range of about 25 to 70%. There are some that are higher. I mean, 100%. You take that with a little bit of a grain of salt. It just means that there's probably a very high fraction of that freshwater component is being derived from the high-level system relative to the local precipitation. But in general, what we're seeing is that the numbers are within the park are between about 25 and 70% being derived from the high-level system. Now, our analysis did not, well, it looked at the three end members, but there are at least a few complications. One is that some of the high-level groundwater is being applied over the coastal freshwater lens system in the form of irrigation, or you might have some pipeline leakage, or even septic system leachate. We did a water budget analysis a few years ago, and that indicated that the component of water derived from those other sources, other than rainfall, probably amounts to on the order of 10 to 15% of the recharge over the freshwater lens system. So you can see that those numbers, that 10 to 15% is less than the numbers that we're seeing in the samples in the park. So yes, there may be a component of irrigation water or septic leachate in the coming into that coastal system, but it's typically on the order of 10 to 15%, not enough to explain what we're seeing in some of these samples. Okay, next slide. Okay, so clearly there's still some uncertainty in what we know about hydrologic conditions in Kona. Some of the data needs that we've identified are that it would be very useful to drill additional wells to help constrain the spatial extent of that deep freshwater zone, and it'd also be very useful to help us better define the conceptual model of the groundwater system. Additional geophysical studies would potentially provide insight into the hydrogeologic setting. And another thing that would be very useful, and I was talking with Joe Fackrell about this earlier, is that it would be great to have a long-term data set of rainfall in the area. Joe is planning to stop collecting his rainfall data, and he was thinking it'd be good if someone else could, take on that duty. Next slide. So to summarize what we found, the existing information that we have, the available information is consistent with some degree of hydrologic connection between the high level and the coastal groundwater systems. The isotopic composition of the fresh water that we find in samples from the park indicates that about 25 to 70% of the high level of the fresh water is derived from the high level groundwater system, but maybe 10 to 15% of that may be derived from irrigation or septic systems. And finally, additional wells and data would definitely help us to improve our understanding of what's going on in Kona. Next slide. Okay, this is my final slide. It describes, lists a few of our recent publications and some of our planned publications. Chip Hunt from our office, he did this work actually quite a while ago, but he's going to be coming out with a report within probably a couple of months describing nutrient and contaminant sources at the park. We also recently published with Fred Tillman and Adam Johnson and myself, we published an open file report which just summarizes the data that we collected. We've also put together a manuscript kind of with our interpretations of the data and our analysis, kind of what I described today. We submitted that for publication, and we're still awaiting a final word on that. And finally, I've listed on the bottom there that we're working on a numerical groundwater model. The study that I talked about today doesn't answer any questions about will pumping in the high-level system have any effect on the coastal system. That's what we're trying to address with this numerical model. And the numerical model is also actually a very useful tool for helping to constrain what's actually going on in the groundwater system. It's been a little bit of a struggle, but hopefully we'll get that done in the fairly near future.
Can you, sorry, that last slide, the numbering study and effects on cooling up groundwater from above, how that may affect or discharge.
Right.
You said is being reviewed for publication, or you'll be able to share it if it's not done?
No, that's not done yet. Yeah, that part of the work has not been done yet. Hoping to have that done within the next year. Said that before.
And again, very little data on the size of the groundwater resource. I mean, on the high level resources. High level water.
Very little data on.
On the actual amount of size. Okay, we know there's some connection, but we don't know that.
Well, we're limited in our information by what wells we have there. I mean, and that shows it's a fairly extensive system. I mean, the water levels are tens to hundreds of feet above sea level, so it's a pretty thick groundwater body. I didn't mention this, but in looking at the recharge elevations, also, if you consider that an elevation above say 6,000 feet. It's really not a very large land area. It really only, based on the water budget analysis we did, it only contributes about 3 million gallons per day of recharge. So it's unlikely that, that alone is forming the high-level groundwater system. It's got to be some recharge from the lower elevations.
In trying to understand the applicability of the isotope data, I'm trying to kind of put it in a perspective of whether this is something that one would want to try to fine tune and get more definition out of, or if what it's really telling us is whether there is a connectivity or not a connectivity, which it seems to be saying quite clearly that there is a connectivity. Is this the kind of tool that, I mean, we want to try to get greater definition by more sampling points to define that connectivity, or is it more, you know, the way it's been used in other places, you know, just more a tool to say there is connectivity, or, you know, if it were not the case, there were no connectivity?
Yeah, I mean, well, the more data you collect, I think the more you're going to converge to, you know, a kind of a better answer, a more quantitative answer. You know, we only collected a limited number of samples from a limited number of places, so it's not, you know, we can't say, well, there's exactly X percentage of that water is derived from the high-level system. So we're stuck with saying that it's kind of a range. But yeah, more samples you collect over time, you probably start reducing that uncertainty.
It's a map that shows like the water flow off the real time. Some sense. In other words, if you could construct a SWOT map, ellipse from the ankle-line ponds to know how water migrates from one geographic area toward those for the National Park Service. Can you construct something like that?
We haven't done that yet, but you could do that with a numerical model. You can kind of derive where that water is being, you know, where it's sourced from.
You see like a 1, 5, and 10 year isotope migration, if you will, back in time.
Yeah, you could do that if you had a good enough model.
I think Milton.
Yeah, Delwyn, in the area that you're talking about, there are no wells in the basal aquifer. Everything comes from the high-level aquifer, which means that everything on the ground there is from the high-level aquifer, whether it be irrigation, whatever, because there is no wells in the basal aquifer in that area. The other interesting thing, and the reason why you're probably finding a lot of that fresh water, is, as you know, the wells in the high-level aquifer varies in depths, which means there must be leakage through the whatever's causing it. Because if there wasn't leakage, you'd have springs popping up all over the place, right? So there has to be leakage.
Mm-hmm.
So naturally, that leakage is going to find its way onto that area. So the fact that your isotope thing shows, what you said, 15 to...
It's about 25 to 70% of the freshwater component of our samples is derived from the high-level system.
And based on what's happening there, I think the number is really skewed from the fact that you have leakage and everything being put on the ground is from the high-level aquifers.
Yeah, and we did a water budget analysis which indicated that maybe about 10 to 15% of the recharge over the freshwater lens system is probably derived from some external sources of water, be it irrigation or septic leachate, not rainfall.
I like your idea about, you know, there should be, and I wish there was enough funding, but there should be a whole bunch more deep wells,
Yeah.
like what Tom Nance did,
Yeah, that's a great well.
to prove the, either prove or disprove the theory that the high-level water exits the ocean way offshore.
Yeah, very, very expensive wells.
Yeah.
I'm with you, but
It's
expensive wells.
Yeah. But it should be done. You guys don't have money?
You didn't include strontium isotope analysis. Have you looked at the fingerprinting signal that the strontium talks about? And is it quite consistent with the one that you get from Keauhou?
Well, we did look at strontium isotopes. To me, it wasn't as diagnostic as the water, the oxygen and hydrogen isotopes. It was definitely consistent with a mixing of high level and coastal water and ocean water, but I don't think you could definitively say that there's X% high level water based on the strontium isotopes. So we talk about it a little bit in our paper, which will be published soon, but I'm not going to talk about it here.
Do we have an idea of a time frame for publication
Of
of the four outstanding
well,
papers?
yeah. Well, the top one, I don't know if you have that again. The top one, which was the nutrient and contaminant sources, that one is actually going to be published probably within the next couple of months. It's gone through our process. It's just being laid out right now. So it's just kind of the last stages. The second one is what I've shown on the left. It's just a data report. It summarizes all our data. It's actually out already. The next one is a paper we submitted to a journal, and we're still waiting for word on final acceptance on that. And then the bottom one is the numerical modeling work that I'm doing, and that's a little bit off in the distance.
Oh, like how far and is it funded?
I want to finish it within the next year. It's a little bit overdue, but we've kind of pushed it back to allow us to take advantage of some of the information that we're gaining from this study. But yeah, I want to get it done.
Do you need more data points for the numerical model, or just to do the work?
Well, I mean, I can do the work with what we have. More data points are always great, but of course that always pushes it back even further. So, I mean, I have what I think I need to at least develop a model.
And what's the scope of the numerical model, the geographic scope?
The geographic scope is I'm mainly concentrating on the coastal system. I'm not going to model all the way inland to the peak.
Head and shoulders.
No, but I am modeling the flux from the high level system downward, and also trying to simulate that deeper freshwater zone. I'm not going to model the whole Keauhou Aquifer system because I think something different is going on further south. So I'm kind of cutting it off a little bit, kind of in the middle of Keauhou.
Where are you going up north?
I'm going north up to the northwest rift zone of Hualalai, and taking it south, not all the way down to the southern extent of Keauhou, kind of in the middle. Yep.
So based off of where you're at in that work, and I guess your own professional opinion, is there evidence now that existing withdrawal, land withdrawal, is affecting freshwater sources from entering the ocean?
Well, if there is a hydrologic connection between the high level and the coastal system, if you pump the high level system, the laws of physics demand that there's going to be an effect on the down gradient system. Now, the magnitude of that effect, we don't know yet.
And if it's being affected currently, we're not sure.
It's hard to say. I mean, it does take a while for that effect to manifest itself, just because the groundwater system doesn't happen instantaneously, water flow.
Do you have information on the migration time period from coastal water to ocean?
No. In terms of travel time,
Right.
no.
Is there a way?
I mean, there's ways to estimate it based on like groundwater principles. So we can come up with an estimate.
Is there a way to do a tracer study or depth dive study or anything like that, or just
You could try. It'd be pretty much a crapshoot though, because tracer studies are notorious for, you don't know where that water's going to come out. So you have to be lucky. Milton?
Is there a simple and inexpensive way of doing an offshore profile to see how much of the high-level aquifer is actually exiting into the ocean, or if in fact it is?
Well, you can take a salinity profile as you go down the bottom of the ocean, and in fact, Nelha has done that. I don't know if Keith's here. Yeah, I mean, they have done some data. When they inspect their pipeline, I believe you collect salinity data also with that. Connectivity, yeah, and temperature. So they've done that with a submersible.
What's the result?
It just shows it gets very cold. Yeah, I don't think it showed any big blip in terms of salinity. I mean, it's all pretty much salty water, but it shows it gets very cold in the deep ocean.
Is there a way to look at the isotopes at different levels?
Sure, if you could, yeah. The problem is you just got to get the samples from the different levels. Use radon.
In your, the type of research that Tom Nance did, or anybody else planning to do that?
What type of research?
Deep wells in the basal aquifer?
Well, I think the state has plans to try to refurbish one of their existing wells. Is that right, Roy? Your Keauhou deep monitoring well?
But the Keauhou is in the high level aquifer.
No.
No.
It goes to the basal, and into the salt water, and then it gets
Where-
fresh water. It's
where's
like
the
the
base?
Kamakana water. They'll show one of the, I think one of your graphs was showing the comparison between the two.
I showed Keauhou well.
Yeah, or Kahu.
Yeah.
Oh, okay.
It's in the basal
Yeah,
aquifer.
yeah.
700 feet elevation.
How much?
700, right?
722.
But other than that, I don't know of any other wells on the books currently to be drilled. I don't know, maybe Thomas can drill a well out here. You got your own drill rig now, so.
Yeah, just, Joel and Steve, this is really good work, and it's really appreciated, and I think it's relevant. So thank you.
Thank you. Kanani, you have a question?
You know, I mean, a lot of this just went over my sunburned forehead.
Sorry.
But I understand that this is really knowledge construction as we go forward and we fill in a portion of the jigsaw puzzle that we're all trying to construct together. And so, as you look upon your results and know that you're publishing in the future and what your next steps are, what are those indicators? What are the indicators for you in your scientific mind when you look at all of this new data? What if you had all the money in the world? What would you do to study the next step?
I would drill more wells. Yeah, and that's the hard data you can get.
Where?
You could drill a transect down Hualalai. I mean, if you're dreaming big, just drill them at different elevations.